In this video I'm going to show you how you can make a wobbling screen effect in Unity. I will first show you a method that works with the built-in renderer, and after that I'm going to show you the necessary changes to make to also make it work with the universal render pipeline. In short, URP. Hey, what's up? Back in 2020 I released my first mobile game called Flight to the Rescue. And in this game there are situations where our hero can get dizzy. And to make the player feel that the hero is dizzy, I added two things. One, I inverted the already inverted controls. Yeah, I know, everybody's favorite. And two, I created a screen wobble effect by moving the screen pixels in a wave-like way, using a fragment shader. But before I show you how to write such a shader to create this effect, we first have to really understand what exactly is happening here and how we can create this wave. And for that we're going to need a little bit of math to... Hey, come on! I keep it simple, I promise! Brr. And if you're not interested in math, you can just skip to the coding part of the video in the next chapter. Alright, then let's start with how to make a wobbling screen effect in Unity. Okay, let's look closely at the still frame of my game. We see that while the wobble effect is active, all the pixel colors are shifted to create a waveform. But they don't just stay in place, or else with our game active, our current wobble effect would look like this. But instead the wave itself shifts vertically, as seen here, to create this wobbly motion. Okay, so how can we represent this mathematically so that we can implement it in our shader? Easy. For the waveform we can simply take a sine function. Or a cosine function, whichever you like. But let's say we use the sine function. The distance between one full up and down wave is called a period. And in a regular sine function the distance of a period is 2 pi. But when working for example with texture coordinates, we don't use coordinate values like pi or 2 pi, but instead use values from 0 to 1. So to make it easier for us, we're going to map this wave in x direction from 0 to 1. To do that, we just multiply the regular period value of 2 pi to our x value, and we have successfully mapped one sine wave from 0 to 1. Now to increase the frequency of our wave, meaning how many times we want to repeat one up and down sine wave in our interval, we just multiply 2 pi x with the frequency we want. So if the frequency is 2, the waves are doubled, 3, tripled, 4, quadrupled, and so on. We're nearly done, only 2 values left to explain and we can start the code. Now to be able to change the height of our waves, we can multiply a value called the amplitude to our sine function. This value will scale our waves to the size we like. For example, if we only want our waves to be half as high, we set our amplitude to 0.5, and so on. Okay, so we have as many waves as we want with the size we want. Now to create the wobble effect, we need to move our wave in one direction. To do that, we just add a shift value to our x value after it got multiplied by the frequency and 2 pi. And to move our wave, we increase our shift value over time. Alright, we are done with the math part of this video. And this is the final function we are going to implement to create the wobbling screen effect. Okay, enough math. Let's now open up Unity and finally start implementing the wobbling screen effect. Okay, so in Unity I first set up a small scene so that we have something interesting to wobble. Now we create a material called WobbleEffect material and an unlit shader called WobbleEffectShader that we will give to our material. Okay, let's now jump into our shader and implement the wobble effect. In our shader, we scroll to the fragment shader, because we want to manipulate the pixels seen on the screen to create this wobble effect. Now, let's look at our function we want to implement. Okay, frequency, shift and amplitude are the variables that we want to be visible outside of our shader so that we can set and change them in our scripts. So we're going to first define them here outside of our fragment shader, and then to make them visible outside, we need to define them as properties. To do that, we scroll up here to our properties and first write the name of our variable. Let's start with frequency. And in brackets we write the name of the property visible outside of the shader and the type. And finally we set the default value of our property. Now let's also do this for our shift and our amplitude. If we now look at our material, we can see our properties we have defined in the properties section and can later set the values of these properties in our code. Okay, back to the fragment shader, we just need to create our pi variable. I just take the first 5 digits after the dot. And we are done setting up all the variables we need. Okay, before we start, let's take a look at our basic fragment shader. Currently it does the following. It gets the UV coordinates for each pixel, looks up the color value in the main texture, which in our case will be the rendered scene of our main camera, and returns the color for the pixel to be rendered then on screen. So basically, what color comes in, comes out. What we want to do now is to shift the colors according to our sine function we defined before. Meaning that we have to calculate a new v-coordinate to get our color from and then return that color instead. So our new v-coordinate is our old v-coordinate plus the value we get from our sine function. Hey everyone, it's me again, the me from the future. What I realize now is that our wobble mirrors our sine wave with this approach. What do I mean by that? Our current pixel gets its new color from the new calculated position according to our sine wave. Meaning that when the sine wave goes down, we replace our old pixel color with the new color from below. And when the sine wave goes up, we replace the pixel color with the color from above. Which in the end, after having processed each pixel, will mirror our sine wave. So to push the pixel colors in the direction of our sine wave, we have to subtract our function from our old v-coordinate. So our new color will be chosen from the opposite direction and therefore will be pushed in the direction of our sine wave function. But don't worry, either way the wobble effect will look the same, because by shifting our sine wave over time, our pixel colors will wobble up and down. So it won't matter if the sine wave is mirrored, because the only thing that is different is the starting position of our wobble. And that's it. Okay, so with that out of the way, let's continue. Okay, let's implement that. From our i.uv, we can access our uv coordinates with x for our u coordinate and y for our v coordinate. Now we first create a new y variable that is the old y variable plus our function we defined before. And after that, we just need to set the y value of i.uv to our new y value and we are done with our shader. And just so you know, this shader will create horizontal waves. If you want vertical waves, like in my game, you can for example just swap the x and y variable, like this. And also don't worry about our v coordinate reaching values lower than 0 or higher than 1, because our uv coordinates will be automatically kept to 0 when lower than 0 or 1 when higher than 1. Okay, now back in the editor we create a WobbleEffect script for our main camera and create a public material variable called WobbleEffectMaterial, which we will set with our created WobbleEffect material in the editor. In our WobbleEffect script, we now have to implement an event function called onRenderImage, which has two parameters, source and destination. Source is the render texture we get after our main camera has rendered the scene, and destination is the render texture we want to basically replace our source with to render on screen. So to use our WobbleEffectShader to change our source and save it into our destination, we use a function called blit, which gets the source, the destination, and the material containing our shader as an input. But wait! Before we continue, I have to inform you that onRenderImage will only work when using the built-in renderer. If you're using URP, this won't work. But don't worry, you can follow along with all the steps in this video, and in the end I will show you the changes we need to make in order for it to work with URP. Okay, with that out of the way, let's continue. Okay, let's see how that looks like now. Seems like nothing is happening. Let's open up our material. We see here that our amplitude is 0, meaning that all our waves are flat. Rising it to something above 0, for example 0.05, will reveal our sine wave. And if we want more waves, we just need to increase our frequency. And finally, with our shift, we can move our wave. Nice, now let's extend our WobbleEffect script to make our screen wobble automatically. First, we're going to create a WobbleActiveBool variable to check if we should wobble or not. Then 4 float variables, one for our frequency, our shift and our amplitude, and one for our shift speed. I set the frequency to 4, shift to 0, amplitude to 0.05, and shift speed to 5. But you can set these values however you like, depending on the number of waves you want, the height, and how fast you want them to move. Okay, next we write 3 functions to change the values of our property in the wobble shader. To be able to set the value in our shader, we need to call the setFloat function of our wobble shader material, and then first give it a string of the property name we want to set, for example here it's frequency, and then the value we want to set. And let's repeat that for our other properties. Now let's write a public start wobble and stop wobble function to set our WobbleActiveBool to true or false. Okay, now that we finished all our preparations, we can write our wobble coroutine to make our waves move. First, we are going to set our three properties frequency, shift, and amplitude. Now, while our wobble is active, we are first going to increase our shift value by time.delta time multiplied by the shift speed, then update our shift properties in our shader, and finally yield return null so that we don't get stuck in our while loop. When we are done wobbling, we set our shift back to 0 and then disable our script to disable our effect. And that's it for our coroutine. Now we just start our coroutine in our start wobble function, and we are done with our WobbleEffect script for now. Now to test this, I'm going to write a WobbleTestManager script that gets a reference to our WobbleEffect script and waits for keyboard inputs to either turn the wobbling effect on by enabling our WobbleEffect script and call its start wobble function, or to turn our wobble effect off by calling the stop wobble function. Hey, future me here one last time. What I've recently discovered is that it does not matter if the WobbleEffect script is enabled or not. It is still possible to call our start wobble function even though the script is disabled. And also, if the wobble is active, it will continue to wobble even if we manually disable the script in the editor. But why is that? This is because disabling our script does not really disable it, but rather disables certain functions of mono behavior, like start, update, fix update, and so on. And therefore, since we will not use any of these, disabling our script won't have an impact on our wobble effect. So what I'm saying is that you can basically ignore these two lines in our code. The one in our wobble coroutine, where we disable our script, and the one in our wobble on function, where we enable it. Okay, that's it. Now back to the present. Okay, now let's test our wobble effect. Nice, wobble on starts our wobble, and wobble off instantly disables it. But look what happens if I press wobble on multiple times without turning it off first. The wobbling gets faster. Why is that? It is because when we turn our wobble on, we always start a new coroutine that runs with all the other coroutines that were created before. And each coroutine we start increases the shift value in its while loop, so our wobble gets faster and faster. To fix that, we just have to check if wobble active is false before we can start a new coroutine, and now we can press on as much as we like without breaking our wobble effect. Okay, the base wobble effect is finished. But if you like a more smoother transition between on and off, like I have for example in my game, we can do this by slowly increasing our amplitude from 0 to the value we like when starting the wobble, and slowly decreasing it to 0 when we want our wobble to stop. So, back to the WobbleEffect script, we are going to set our amplitude to 0 and create a max amplitude variable that holds our highest amplitude value. And we are also creating an amplitude speed variable that defines how fast the transition between 0 and max amplitude will be. Now, in our wobble coroutine, we're going to squeeze ourselves between set shift and set amplitude and are going to implement our wobble warm-up phase as follows. While amplitude is less than our max amplitude, we are going to increase our amplitude by delta time multiplied by the amplitude speed to slowly get bigger waves with each frame. Then we are also going to increase shift by delta time multiplied by the shift speed to move our waves. And after that we update the amplitude and the shift in our shader and end the loop with yield return null. Outside of the loop, we then set amplitude to its max value and update our shader one last time before we get to our main while loop. And we are done with our wobble warm-up. Now the cooldown part is similar to the warm-up. After our main wobble effect loop, while amplitude is less than 0, we decrease our amplitude instead of increasing it, to slowly flatten out our waves. The rest stays the same as in our warm-up while loop above. And outside of the loop, we set amplitude and shift to 0 and update our amplitude in our shader before disabling our script. And that's it. Let's see how that looks like. Nice, now we have a smooth warm-up and a smooth cooldown of our wobble effect. But what happens if we try to start our wobble while the effect is in cooldown and vice versa? Okay, so when we press wobble off while warming up, we see that our amplitude will rise until its max value and then directly after start cooling down. This makes sense because our stop wobble function sets our wobble active variable to false. And when warming up, we don't check if it is false. So it will complete the warm-up phase and only then check here if wobble active is false before starting to cool down. Okay, and what happens if we press Wobble On while cooling down? It locks our amplitude. This is because when we are cooling down, our wobble active is false. This means when we call the start wobble function, we are allowed to create a new coroutine and warm up again. And because our cooldown phase decreases our amplitude until it reaches 0, and our warm up phase increases our amplitude until it reaches its max value at the same speed, we get stuck. Okay, so let's fix this. To be able to end our wobble while we are warming up, and start our wobble again even if we are cooling down, we have to actively check our wobble active variable in each of our phases. So in our warm up, we only continue to warm up if wobble active is true. And if it is not, meaning if we press wobble off in the meantime, we break out of the while loop and stop the whole warm up process. And let us not forget to also check here in our last warm up step if wobble active is true, or else we would accidentally max out our amplitude. Okay, our main wobble loop here is fine as it is, so let's move to our cooldown. Here we handle things similar to our warm up. We cool down our wave effect only if wobble active is set to false, else we stop immediately. And also here we only do all this if wobble active is false, because if it is not false at this point, it means that we have activated our wobble again, so it would be a bad idea to change our values and disable our script. One thing I realize now is that when setting our amplitude after we increase it, there is a chance that amplitude is greater than max amplitude. So I just put this up here before we increase our values, and that fixes it for our warm-up. And the same goes for our cooldown. Here I also have to change the order, or else there is a chance that our amplitude gets below 0. And while we're at it, we can remove set shift here, and instead set it here at our last step before disabling the script. And finally, let's just move this set shift up here, so the order is consistent with the other while loops. Okay, let's take a look at how our effect looks now. Thanks to our changes, we can now smoothly start and stop our wobble at any time. Nice, basically that's it. We finished our wobbling screen effect. There's only one thing I like to mention. If you're worried about the shift variable getting too big when our wobble effect is active for too long, don't be. We're using float, so the value can get pretty big before reaching its max value. But I still saw some strange behavior of our shader when reaching a value of, for example, 10 million. So to be extra sure, we could reset our shift to 0 whenever it reaches a value of 2 pi. Why 2 pi, you ask? This is because the period of a regular sine function is 2 pi. And since our shift value is not multiplied by the frequency and by 2 pi, we get one full up and down wave when increasing our shift from 0 to 2 pi. So, back to our code, at each point where we increase our shift value, we can use the modulo operator to limit our shift values from 0 to less than 2 pi. And as you can see here, our shift value gets set back to 0 whenever reaching 2 pi. But our wobble effect still looks like before. Okay, great. Now, as promised, I'm going to show you a way to make this effect work in URP. When looking at Unity's documentation, Unity suggests that for URP we need to use the ScriptableRenderPass API, because OnRenderImage is not supported. This means, to be able to use the blit functionality we use in the OnRenderImage function, we need to write our own renderer feature. I won't implement this renderer feature here, but instead I'm going to use code I found in an article by Bill on GameDevBill.com, who originally took the code from another article written by Sine on sinegamedev.wordpress.com. I will link both sites in the video description for everyone who is interested in reading more about this topic. Okay, now, in Unity I've created a URP project with the default sample scene and added all the code and game objects from before. Now we're going to copy the blit code, go back to Unity and create a script called blit. And in the script we delete everything and paste the code we copied earlier. In our universal render asset we select add renderer feature. And there we see our created blit. We select it and give it our wobble effect material. You can see that the effect now is already applied to our scene, but with some strange artifacts. This is because our blit is applied too early. To fix this, we go to Event and select Before Rendering Post-Processing. And now everything looks fine. Let's now disable blit and start implementing the necessary changes in our code. In our WobbleEffect script, we can safely delete our onRenderImage function, or comment it out, if you want to keep its memory alive. Now, to be able to control our renderer feature, we need to first add that we want to use the Unity engine.rendering.universal namespace, And then create a public scriptable renderer feature variable that we're going to set with our created blit renderer feature in the editor. In the start wobble function, we then activate our blit renderer feature before starting our coroutine. And in our coroutine, we disable our blit renderer feature instead of the WobbleEffect script when we are done wobbling. And because we won't disable our WobbleEffect script anymore, we don't need to enable it in a WobbleTestManager script. And that's it! The only thing I'm going to change now is the keyboard input here, because the A key is already used in this URP sample scene. Okay, then let's test it. Nice, now our effect also works with the universal render pipeline. I hope you liked this video, and if so, why not give it a thumbs up? Do you have some questions or some tips on how to improve this method, or simply just want to say hello? Then why not write a comment down below? I'd love to hear from you. And thank you so much for watching, and until next time, ciao! Yo! Before I forget it, if you'd like to see more tutorials or tutorial-like videos, then check out this one, where I show you how I make a retro shattering screen effect for a private project of mine. And if you'd like to see more of my mobile game where I first implemented this wobbling screen effect, then you can check out all the videos related to it here. Or if you like, why not check out the game out for yourself? You can download it for free, the link is in the video description. Okay, that's it, bye!